Hi, and welcome to Dr. V's AP Chemistry webcast. In this webcast, we're talking about multiple ionization energies and the trends that we see with those. Here's what I'd like to accomplish in this webcast. First, I need to introduce this idea of multiple or successive ionization energies. And then we need to talk about the trends that we see when we have multiple ionization energies. And finally, some practice problems using them. Now, when we introduce ionization energy in our first year courses or early in this unit, we often focus on the first ionization energy, the amount of energy required to remove the outermost electron from a neutral isolated gas phase atom. We can write an equation like this. Our neutral atom A, we put in a certain amount of ionization energy. We get a cation with a charge of +1 because we kicked out one electron. That's the first ionization energy. But if we add more energy, we can remove a second electron, and this amount of energy is called the second ionization energy. So I had to remove a second electron, but I'm doing it from the cation with a +1 charge. So I'm taking my cation with a +1 charge, putting in a certain amount of energy, and I'm making now a cation with a +2 charge. So we're removing one electron at a time. Now, you can actually have as many ionization energies as there are electrons in the atom, and I want to give a shout out to my friend Mr. Millikan who shared this graph with me. We can have a first ionization energy, a second ionization energy, and so on, one for each electron. So for sodium, we could be talking about 11 ionization energies. So what I did is I just pulled out the graph of multiple ionization energies for sodium. And we can see as we go from the first to the second to the third ionization energy that each successive ionization energy is larger than the previous one. So that's why we're seeing this go up, because we're going from the first ionization energy in light blue, that very low one, to the seventh ionization energy in the navy blue. Part of the reason for this is that as we continue to remove one electron in each step, we're going to have fewer electron to electron repulsions. And so it's going to become a little bit harder to remove the electrons. But that's not the only factor, and we'll talk about that on the next slide. Now, if we continue looking at the multiple ionization energies, it becomes apparent that once you've removed all of the valence electrons from an atom, there's a very large increase in the ionization energy. We're going to look at some examples of this. Let's start by looking at the multiple ionization energies of sodium, which I've got highlighted here in this table. We know that sodium has one valence electron, and that valence electron is located in the 3s sublevel. And so it takes a certain amount of ionization energy to remove that 3s electron, 498 kilojoules per mole. Okay, but what if we want to remove that second electron, right? So that's IE2. Now, that second electron would have to be removed from the 2p sublevel. So by removing the valence electron, we've actually lost an entire energy level that's no longer occupied. And so we have fewer occupied energy levels, and the electrons in the 2p sublevel are closer to the nucleus, and they're going to experience a stronger Coulombic attraction to the nucleus. And therefore we see a very large jump from ionization energy 1 for sodium to ionization energy 2 for sodium. It's about a 9-fold increase. That's really a big change in ionization energies, but that's consistent with sodium having one valence electron. Okay, so does the pattern hold? We had other information in that table. So let's think about magnesium. Now we know magnesium has two valence electrons, and of course these two valence electrons are both in the 3s sublevel. So if we look at the table and focus on magnesium, the first ionization energy of magnesium is 736. The second one is 1445. So it's about a 2-fold change to go from IE1 to IE2. So losing the second electron is also coming out of that 3s sublevel. But when we go to lose a third electron, now that ionization energy, IE3, is quite a bit bigger than IE2. And that's consistent with magnesium having two valence electrons. Losing the first one took a certain amount of energy. Yeah, it takes more to lose the second one. It's about a 2-fold change, as I said. And it's about a, 6 or 7-fold change, just off the top of my head, for IE3. Because to remove that third electron from magnesium, I now have to go to my 2p sublevel. So we see this big change in ionization energies as we go from 1 to 2 to 3. Does it hold up? Let's look at aluminum. Aluminum, we know, has 3 valence electrons. There's one in the 3p sublevel, and then there are 2 in the 3s sublevel. So losing the first valence electron, 577. Okay. Losing the second one, of course, that's an increase. Losing the third one, that's an increase. We would expect to see a very large increase between IE3 and IE4. Now, we don't have that data, but it is quite a bit bigger, because now we're having to remove an electron from the 2p sublevel. We can use this kind of reasoning where we're looking for big changes in successive ionization energies to figure out the number of valence electrons to solve several different kinds of problems. Here's the first one we'll do together. The table shows successive ionization energies for element X. And then the problem goes on to tell us that element X is in period 2. And the question asks, based on the data, how many valence electrons are present in an atom of element X? So we're going to look at the successive ionization energies, going from the first to the second to the third. They're increasing, that's what we expect, to the fourth to the fifth. Nothing dramatic yet. Fifth to the sixth, that's fine. Oh, but look at the change between the 6th ionization energy and the 7th ionization energy. I'd say that's a pretty substantial change. That's a huge jump. And so what that tells us is that I can remove the first 6 electrons with just incremental changes in the ionization energies. But trying to remove a 7th one as that big jump in the ionization energy, I must now be at a noble gas-like configuration. I've got 6 valence electrons in atom X. And therefore, I can conclude, since I know it's in period 2, that this must be oxygen. Okay, let's work through another problem. I changed the color coding of the table so it really does show up as being a separate problem because the formatting on the side is pretty much the same. The ionization energies of unknown element Z, which is also a period 2 element, are shown in the table. And the question asks, based on the data, what is the formula of the compound form between strontium and element Z? All right, so let's look at these successive ionization energies. First to the second to the third to the fourth, all nice incremental changes, the fourth to the fifth. Seems pretty reasonable. Wait a minute. We look at the difference between the 5th ionization energy and the 6th ionization energy. I'd say that's a very substantial change. Therefore, because we have that huge jump between IE5 and IE6, that's telling us that I have 5 valence electrons. Because I can remove the first 5 relatively easily. But the huge jump to remove a 6th electron tells me that that 6th electron is in a lower energy level, probably a noble gas-like configuration. And therefore, element Z must have 5 valence electrons. Now, if you know your periodic table, and of course you do, we know that an element with 5 valence electrons is likely to form an anion with a charge of -3. This is significant because I want to know what formula it would form with strontium. And of course, strontium, being an alkaline earth metal, typically forms cations with a charge of +2. So I need Z to be forming an anion here to make this ionic compound. And therefore, I can conclude that the compound formed between strontium and element Z would have the formula Sr3Z2 to give me a neutral formula. All right, so let's summarize what we've talked about. We can report and measure successive ionization energies for removing each electron from an atom, removing one at a time, working from the outside in. It gets progressively more difficult to do this, and the ionization energies increase as we go from the first to the second to the third ionization energy, and so on. And we can use this data to determine the number of valence electrons in an atom and what typical ion charges that element would form. If you haven't already done so, I encourage you to subscribe to my channel so you get all my latest videos. Have a great day, everyone. We'll talk another time.